Alright, here's another ring theory problem. So we have our ring here, and it's just polynomials with integer coefficients. We mod out by the ideal generated by x squared plus 1. Prove or disprove that R is a PID. Well, it is a PID, so we're going to prove it. So the first thing we're going to prove is that R is isomorphic to the Gaussian integers as a polynomial. So Zi, this is just all things of the form A plus Bi, where here both A and B are integers. Anyways, so to make it easier to write all of this, let A be the ideal generated by x squared plus 1. And so R is just Z polynomials in X mod out by A. Now define a map from R to the Gaussian integers, which sends the polynomial coset P. You take a polynomial P of X in Z of X, and we add A to it, and we send this to P of I. And I claim that this is a ring isomorphism from R to Zi, which confirms that these two rings are isomorphic. So we have to, the first thing we have to prove is that this map is well defined in the first place. Oh, by the way, I think there is a slick way to prove this part using like the ring isomorphism theorems. But I think there are some details in that aren't like completely obvious, and this just seemed like an easier way. Also, I think at this level of course, I don't think it's necessary to prove this in as much detail as I'm going to. Like I know, at least for the professor I have, he'd probably be fine with by undergraduate algebra, we know that these two things are isomorphic, but I wanted to take some time to actually go through this in detail because I tend to err on that side of doing more details. Okay, so I want to confirm that this map is well defined. So suppose P and Q belong to the same cosets. So then there is some R in this ideal A such that P plus R is equal to Q. That's what it means to be in the same coset. Since R is in A, and since A is the ideal generated by x squared plus 1, there is some polynomial S such that R is precisely S times x squared plus 1. But then if we evaluate this at I, Ri is Si times, then we plug in x equals I, and this is I squared plus 1, but this is 0. So then this whole thing is 0. So therefore we have phi of P plus A is P of I, which since R of I is 0, this is P of I plus R of I, but P of I plus P plus R is Q, so P of I plus R of I equals Q of I, and Q of I is, of course, phi of Q plus A, and so if you have two representatives of the same coset, they'll map to the same place, which is what you need to check in order to confirm that phi is well defined. To prove that it's a ring homomorphism, this is really easy. You just take, so when we add, this is what the sum of two elements in a ring looks like. Not in a ring, in a coset. So P plus A plus Q plus A is P plus Q plus A. And then this, of course, is P of I plus Q of I. But then P of I is phi of P plus A, and Q of I is phi of Q plus A. And so, so the addition works for multiplication. This is, of course, the product of P plus A and Q plus A in R. Okay, so this is equal to Pi times Qi, but that's, of course, this. And then, of course, 1 will get sent to 1 evaluated at I, which is just, since there's no x's involved with 1, it's just 1. So, and remember, we need to check this one manually because it's we need to check the multiplicative identity because multiplication is only a monoid. And so we don't know. We know automatically from this that phi of 0 plus a is 0, but from this we have to actually, we cannot conclude from this second equation that phi of 1 plus a is 1. Anyways, okay, so it's a well-defined ring homomorphism. For surjectivity, that's easy, because you take anything a plus bi in any Gaussian integer, and it's just the image of the polynomial a plus bx. For injectivity, this is the tricky one, well, the trickiest. Observe that if you have any polynomial written in this form, phi of this coset is the sum from 0 to n of aj I to the j. I'm sorry, j's and i's, they look similar, they mean very different things. So the powers of I, starting at 0 and increasing, we're going to get I to the 0 is 1, I to the 1 is I squared is -1, I cubed is -I, and then I to the 4th is 1 again, and we get 1, I, -1, -I, 1, I, -1, -I, so on and so forth. So these thingies are all the same after a while. Oh, and this should not be an x, should be I. So this is I. My pen is doing this again. Sorry. I ordered a new pen because what my pen does is it, like, my stylus only needs to be like a quarter of, like, maybe like 3 millimeters from the screen, and it'll start picking up. And restarting everything doesn't work, so I just need to get a new pen. Anyway, so I'm sorry this I to the k looks horrible. Whatever. This should be I to the k. I to the k. Okay, so now we can take this sum and write it as, well, what's going to happen when we evaluate I to the k? We're going to, everything that's equivalent, all the indices which are equivalent to 0 mod 4, it's just going to be that. It's, oh, that was unintentional. If it's equivalent to 2 mod 4, then it's going to be, we're going to have this I to the j is going to become -1. So these are all minuses. Then, of course, if it's 1, then it's going to be I. If it's 3, it's going to be -I. And so we have this I out here for that reason. So yeah, and of course these are all, it's not all j, it's not all integers j which are equivalent to, congruent to 0 mod 4. It's all integers j between 0 and n which are congruent to 0 mod 4. I just didn't want to write all of that out because this is already like more detail than I think most students would write. In fact, this whole segment is more than most students would write, let alone this part of this segment. But anyways, again, just trying to be as clear as I can. So with this in mind, if we define a and b so that the final term in the above equation can be written as a plus bi. So basically what I'm doing is, okay, let's see if my pen doesn't freak out a ton here. So this whole thing will be a, and this whole thing will be b. Alright, so if we do this, then phi of p plus a is going to be precisely a plus bi. And so what that means is that p plus a is going to be a plus bx plus a, because phi of this is going to be a plus bi. Alright, so that's important because we know we can always find an element in any coset which is a polynomial of degree at most 1. And that's really important because now if we have any such p and a and b, so p, we have any polynomial p and a and b are such that p is equal to ab, blah, blah, blah. Then, so we're trying to figure out what the kernel is. So the kernel, so this phi of p plus a is 0 if and only if phi of a plus bx plus a is 0. And that holds if and only if, well, this is a plus bi, so if only if a plus bi is equal to 0. But since this is just a plus bi, this can only be 0 if both a and b are 0. And since right, so if a and b are 0, then p plus a is equal to a. So maybe you could write another step in there if you really wanted to. I don't think that's... Again, this is already a lot of detail. So if a and b are 0, then p plus a is equal to just a. And if p plus a is equal to a, that is equivalent to p being an element of a. So these are all if and only ifs. So p plus a is in the kernel if and only if p is in a. Therefore, the kernel is precisely a. And that's sort of obvious because, well, you do technically have to prove that, but it should be intuitive because we're considering the quotient by a. But anyways, and this is a 0 element of R, because that's a 0 element in the quotient ring. Okay, so therefore phi is indeed a ring isomorphism because it's a well-defined homomorphism which is injective and surjective. And hence, R is isomorphic to the Gaussian integers. Okay, so I ran into some issues when I was recording this the first time because this thing here that says Zi is a domain, when I wrote this up the first time, for some reason I thought it said Zx. And so I proved that that the polynomial ring with Z is a domain, but that's not relevant. So anyways, we're going to prove that Zi is a Euclidean domain, and we know that Euclidean domains are PIDs, so anyway, since Zi is isomorphic to R, if Zi is a Euclidean domain, then R is a Euclidean domain, and so R is a PID. So we want to prove that Zi is a Euclidean domain. We need it to be Euclidean and a domain. So to prove it's a domain, we know, suppose AB equals 0 in Zi, we can rewrite A as R1 e to the I theta 1, and B as R2 e to the I theta 2. And here, of course, R1 and R2 are greater than or equal to 0, and theta 1 and theta 2 are some angles. So R1 and theta, Ri and theta I for I equal 1 or 2, these can be, or Rj and theta j for j equals 1 and 2. I should be more careful there. These can be, they don't have to be integers, but they have to give rise to Gaussian integers. But anyways, so AB equals 0 if and only if, well, how do you multiply together A and B? It becomes R1, R2, e to the I, theta 1 plus theta 2 because the angles add up. So if this is 0, the only way for this to be 0 is if this part, the R1, R2, is 0. So that's if and only if R1, R2 is 0. But this is in, let's just say it's an R, because I'm not going to worry about where R1 and R2 could possibly be. We'll just say they're an R. And we know, obviously, that R is a domain. That's standard enough of a fact. I'm not going to prove that the real numbers are a domain. So anyways, R1 and R2 is 0 if and only if either R1 is 0 or R2 is 0. So in either of these cases, the corresponding A or B is going to be 0 because its radius is going to be 0. Doesn't matter what the angle is. So anyways, R1 equals 0 or R2 equals 0 if and only if A equals 0 or B equals 0. Okay, so AB equals 0 if and only if... Wait. Do I need if and only if? No, I really only need the forward direction here. But that's implied by the if and only if. So I guess the if and only if was a bit of overkill for what we need here. But it doesn't matter. We know that it's a domain because If a, b equals 0, then either a equals 0 or b equals 0. Okay, now to prove it's Euclidean, that's more work. Define a function delta, which takes polynomials to... No, Gaussian integers to integers greater than or equal to 0. And we're just going to send it to the norm squared, which is a squared plus b squared. So note that this is multiplicative, and I just go through and work this out. This thing is, well, this is what it is, and so it's these two things squared. And then here we'll get this term, and they'll cancel out, so we'll be left with these squared terms, and you move them around a little bit. And this is a squared plus... It turns out this is a squared plus b squared times c squared plus d squared if you FOIL it. And then these individually are just deltas of things. So, yeah, basically delta is it's sort of a morphism under multiplication. Anyways, okay, so let alpha be in Zi and beta be a non-zero element of Zi. So we want to prove that there exists Q and R in Zi such that alpha is Q beta plus R, and either R is 0 or QR is, or the size of R is less than the size of beta. Basically, we're taking alpha and dividing by beta with remainder. And of course, this remainder must have size less than the size of beta. Or it's, well, yeah. So really what we could just say is delta R is less than delta beta, right? Whatever. Okay, so since beta is non-zero, and we know that if we adjoin I to the rationals, then we get a field, and therefore there is some inverse to beta in the rational in this field of basically Gaussian integers, but instead of integers you have rationals. So Gaussian rationals? I don't think that's a thing, but I'll call them that maybe. Anyways, so then we know that a times beta invert. Well, a being in the Gaussian integers is going to be in the Gaussian rationals. So this whole thing is in the Gaussian rationals, and we can write a times b inverse as x plus yi, where x and y are rationals. So now choose c and d in Z such that the distances between z and c and between y and d are less than a half. And we can obviously do that because any rational is at most distance 1/2 away from an integer. And in fact, any real number is at most distance 1/2 away from an integer. And this norm here is, of course, the typical norm in on the reals. So anyways, so take Q to be C plus DI. Then alpha beta inverse is equal to x plus yi. Then what we can do is, if we multiply both sides by beta, we get alpha is beta times x plus yi. X plus yi, we add and subtract c, and add and subtract di. And we get this. And now we can take this beta times c plus di, so we get a beta times c plus di, but that's just q. So this is beta times q. So really what this is beta times q plus x plus yi minus q. And but when we take this q here, we move the c next to the x and the d next to the y, and we get x minus c plus y minus c times I. So anyways, so let R be this whole thing here, and we're going to prove that this is what we wanted. Okay, note that since alpha and beta q are this thing and this thing are Gaussian integers, R must also be a Gaussian integer. That's not completely obvious because, look, we're taking x, and we're taking x, which is just a rational thing, and we're subtracting c, which is an integer. So this thing could be rational and this thing could be rational. But once we multiply it by beta, it turns out this thing needs, multiplying by beta needs to force it to become force the product to be in the Gaussian integers, because you just subtract the beta q from here, and you have r is equal to alpha minus beta q. And of course this is a difference of things in Gaussian integers, so it's in the Gaussian integers. Alright? So if it happens that x and y are both in z, then you choose c and d to be equal to z, you choose c equals x and d equals y by this condition, and then you get x minus c and y minus c are both 0, and that implies that r is just beta times 0, which is 0. Okay, so that's one of the scenarios here. Otherwise, we want to prove that delta r is less than delta beta. So to prove that, we have delta r is equal to delta this whole thing, because this is r, and we know that delta is multiplicative from here is equal to here. And so we have, this is delta beta times delta this whole thing. So this is delta beta times, now this is x minus c squared plus y minus d squared. We know that the norm of x minus c and y minus d are both less than a half, and therefore this is less than or equal to delta beta times, this is less than 1/2 squared, and this is less than 1/2 squared. Well, less than or equal to 1/2 squared. So we get 1/4 plus a fourth, which is a half. So this is delta beta over 2. And this is going to be strictly less than delta beta, and that's because beta is non-zero. So basically one of the either the x-coordinate or either the real coordinate or the complex coordinate will be non-zero. Which means that delta beta is going to be strictly positive. And since delta beta is strictly positive, dividing by 2 is going to give you a strictly lower number. Okay, so therefore either r equals 0, or in the case where r is not 0, we get this equality, delta r is strictly less than delta beta. And that's exactly what we needed up here. And so this is the condition that you need to have a Euclidean, for the thing to be Euclidean. So therefore zi is a Euclidean domain, and hence by the first sentence of this whole paragraph thing, r is a PID. And that finishes part A. Part B, what is part B? We take a prime integer such that the number is congruent to 3 mod 4, and prove the ideal generated by P is a prime ideal in R. Alright, so let's see here. We first claim that in a PID, if Q is irreducible, then the ideal generated by Q is prime. This is sort of a standard ring theory fact, and we'll go through the proof of it. So suppose Q is irreducible in a PID. This means that Q is neither 0 nor a unit, i.e. it doesn't have a multiplicative inverse. And, well, being unit... Well, okay, yeah, units need to be non-zero. Anyways, and if Q is A times B, then either A or B is a unit. That's what it means to be irreducible, which is different from being prime. Okay, so now suppose, well, is sometimes different from being prime. Sometimes they're the same. In general, they're not. So suppose A times B, the product is in Q. We want to prove that either A is, well, the ideal generated by Q. We want to prove that either A is in Q or B is in Q. If A times B is in this ideal, then this ideal is just, well, it turns out this is just products of elements in the PID times Q, because technically it's like finite sums of products of things, but you can factor out the Q from all of them. So anyways, this means that there's some element R in the PID such that AB equals QR. We know that Q is not a unit. And so QR cannot be a unit, because if QR were a unit, then Right. So if QR had a multiplicative inverse, then you'd have like some element C such that C times QR equals 1. And if C times QR equals 1, then C times Q... this should be a very easy fact. I don't know. I'm blanking on this for some reason. Since Q is not a unit, QR cannot be a unit. Oh, of course. The thing here is everything here we're talking about commutative rings. So that makes this really easy because if I say this makes it easy after just taking some time to have to remember how all this works. It's a kind of a common thing in math that happens is once you realize something, it's completely obvious, but it takes time to, it's very easy to forget these quote-unquote obvious things. And so there's a question of if you have to think, if it takes you a while to remember a thing that's obvious, is it really obvious? But anyways, so if QR were a unit, then you'd have QR times C equals 1 for some C. But then Q times R times C equals 1, and so R times C is, okay. So QRC equals 1. So then we have Q times RC equals 1, and that means that RC, and of course RC times Q equals 1, and that means that, well, because of commutativity. And so then Q has a multiplicative inverse, which is RC, and that proves that Q is a unit. But since Q is not a unit, that cannot happen. So Q is not a unit, so QR cannot be a unit, and since QR equals AB, AB cannot be a unit. Okay? Also, okay, so that's this. And since the product of two units is a unit, because you just, the product of two units C times D, if you just, the inverse of that is, the inverse of CD is D inverse C inverse. Or C inverse D inverse, because this is commutative, whatever. So the product of two units is a unit, so if if A and B were both units, then AB would be a unit. So since AB is not a unit, either at least one of A and B must not be a unit. So that's that. We also know that one of A and B must be a unit. Right, because Q is irreducible. So if Q equals A times B, then one of A and B is a unit. So one of A and B is a unit. So therefore, we know that, one of these things is a unit and the other one is not a unit. So if A is not a unit, then B is a unit, and in this scenario we have we can write A as Q times R times B inverse, because B is a unit, so it has an inverse, which means that A is a multiple of Q, and so A is in the ideal generated by Q. Likewise, if B is not a unit, then A is, and so B equals QRA inverse, which means that B is in the ideal generated by Q. So therefore, if A times B is in this ideal, then either A is in there or B is in there. And that's what it means to be a prime ideal. So in a PID, if Q is irreducible, then the ideal generated by Q is prime. So that's good. So now let's prove the thing that we want to prove. Okay, so let P be a integer, and let it be prime, and let it be congruent to 3 mod 4. We know that R is a PID, so then if we think of this ideal as an ideal in Yeah, this is sort of there's sort of it's we're sort of being loose with our rings because when you think of the ideal generated by P, you're implicitly imagining it because P is an element of Z. You're implicitly thinking of this ring R as if it's Z adjoined, as if it's isomorphic. You're thinking of R as the Gaussian integers. You can do that because they're isomorphic, but it's sort of abusive notation. I really don't like this whole being loose with notation. On the plus side, it makes problem statements easier to it makes problems easier to state, but it's more work to the it's more work for the person trying to do the problem, which makes sense since I'm not the one who has to write the problems. I'm the one who has to do the problems. So for me, it makes sense that I would not like something that makes me have to do more work. Well, I guess you don't. It's not that I have to do more work. It's just that I have to think more, which I guess is the whole point of this. Anyways, so we can do this. So to prove that this ideal is prime, it suffices to prove that P is irreducible. And so prime does not imply irreducibility in general. So we have to prove this. So suppose that P is A times B, where A and B is in R. We want to prove. Oh, but what else? P is not 0. Oh, well, P is not 0 because it's prime, and P is not a unit because it's prime. So maybe you should write that in. Maybe you don't have to. But anyway, so you need that in order to as part of the definition for being irreducible. But anyway, so suppose that P is AB, A and B are both in R. Then P squared is delta P, because in the Gaussian integers. So I guess if we want to be super technical, again, this is more on the part of this being more work on my end. So this should really be A and B and Z adjoin I. So anyways, P squared is delta P, which is delta AB, which we know is delta A times delta B. So either delta A and delta B are both P, or one of these two is 1 and the other one is P squared. And that's because P is prime. So that's the only way for two things to multiply together to give you P squared. Alright, so, and also the other thing about that is that, these deltas are always greater than or equal to 0. So, you don't have to worry about, like, minus signs, because that would add more potential cases in here. But anyways, so assume for contradiction that these things are both P. Again, contradiction, you want to avoid this when you can. I think this is the easiest way to do it. Anyways, suppose we write A as x plus yi. So x and y are both integers. Then delta A is x squared plus y squared. Now if x is, okay, so in general, observe that if x is odd, then, no, even. If x is even, then x is 2k for some integer k, in which case x squared is 4k squared, which is congruent to 0 mod 4. If x is odd, then we can write x as 2k plus 1 for some k and z, and so x squared is this squared, which is this, which is congruent to 1 mod 4, because these first two terms drop out. So then, if x squared is equivalent to 0 mod 4, so therefore, since x is an integer, all integers are either odd or even. So x squared is going to be equivalent to either 0 mod 4 or 1 mod 4. Likewise for y squared. Therefore, since delta A is x squared plus y squared, and each of these things can be either 0 or 1, this sum can either be congruent to 0, 1, or 2 mod 4, but cannot be congruent to 3 mod 4. I hate the kerning is off here. LaTeX is a little weird with this mod thing, but I'll probably go back and fix this at some point. but not for the video because I don't want to have to refilm this. This is already super long. Anyways, so P is not congruent to 3 mod 4 because it could only be congruent to 0, 1, or 2. And this contradicts the assumption at the beginning that P is congruent to 3 mod 4. So that's why we use that assumption, because we need it here. What about P being congruent to 4 mod 4? Well, that doesn't exist. Well, yeah. 4 does not exist mod 4. It's just 0. And if it's 0 mod 4, then it's not a prime. Therefore, it cannot be that delta A and delta B are both P. So then one of delta A and delta B is P or is 1 and the other is P squared. So if it happens that delta A is P squared and delta B is 1, then let's see here. I think I'm reusing X and Y here, so this is abusive notation, but sorry. Okay, so if this is in here, then if this is 1, then x squared plus y squared is 1. That's because that's what this is. And this can only happen if one of x and y is 0 and the other is either plus or minus 1. So therefore, x plus yi is going to be 1, negative 1, I, or negative I. These are all units in the Gaussian integers because they have inverses, so positive 1 and positive 1 pair up. So do negative 1 and negative 1. And then you pair I with the one of the opposite sign, because negative I times positive I is negative 1, is negative 1, which is 1. Okay, so delta B is 1. So that means if delta B is 1, we know that delta B is either plus or minus 1 or plus or minus I, which means that's a unit. Likewise, if delta A is 1 and delta B is P squared, then A is a unit. So if P equals AB, then either A is a unit or B is a unit. Therefore, P is irreducible, and hence the ideal generated by P is prime, and that's what we wanted, and now we're done with the proof.